In this lesson, we're going to analyze this compound gear train, and what we're looking at here is gears B and C. They are sharing the same shaft, so this is partly why this is a compound gear train, and we can see that they are also connected to A and D. So there are a few things that we need to first understand before we do the calculations. Otherwise, it will not make any sense. So I'm going to take time to explain these in the next minute and a half thereabouts. So first one is our force ratio. And a force ratio, very importantly, is the same as having a mechanical advantage. So both of these mean the same thing. And our force ratio is directly proportional to our load, but inversely proportional to the effort. And depending on the type simple machine or machine that we have, this will look different in terms of the calculation. So we're going to analyze specifically for this gear train. Now the next thing that we need to bear in mind is this movement ratio, and in some materials you will see known as a velocity ratio. Now this is directly proportional to the distance moved by the effort, and it would be inversely proportional to the distance moved by the load. Now we also have the efficiency ratio, which that is just a ratio of these two, which is the force ratio and the movement ratio. So what I'll do now, I'll just analyze this gear train for you to see what the formula look like if we were to find the movement ratio, or if we were to say, given the force ratio, how would we find the efficiency ratio? So let's do that. Say we were to find the movement ratio of this gear system, then if we were to take the speed of the last gear, which is in this case D, so the speed of D, then that would be equal to the speed of our first gear there, which is A, and that would be multiplied by the number of teeth in A, the number of teeth B, and the number of teeth in C divided by the number of teeth in D. So that would be our standardized equation. Now if we were to rearrange this for the movement ratio, then this is what we would end up with. So then for the movement ratio, we're going to rearrange this entire equation, basically flip it upside down, and what we would have is the speed of A over the speed of D. Now that would be equal to, so now we're going to flip this equation over here, so number of teeth in B over number of teeth in A, and times by, we're just inverting all of these, so number of teeth for D over number of teeth for C. So once we put our values in, then, and that would give us 160 for B over what we have here for A, which was 40, and multiplied by 96 teeth for D and 48 for C. So this leaves us with a movement ratio of 8. So say we were to take it a step further then and evaluate the efficiency of this simple machine. So the efficiency, as mentioned before, is just going to be our force ratio, and that would be divided by our movement ratio. Now the force ratio was given, and that was 6, and we just calculated the movement ratio to be 8, and because it's efficiency we're evaluating here, then we multiply by 100 to get this as a percentage. So as a percentage, we would have here 75%. So that's it. We hope to evaluate other forms of simple machines. So hopefully If you like this video, you can let me know. We'll look at the pulley system, screw jack system, lever systems, and other forms of simple machines. So let me know in the comments if you'd like to see more analysis of simple machines. And until next time, I will see you in the next video.